All right, so now we're going to take a look at a general concept in chemistry that we refer to as nomenclature. When you hear the term nomenclature, you'll see this in several places. This just means naming substances. Okay, and we're going to take a look, first of all, here at basic ionic nomenclature. So the naming of ionic compounds. And we're looking specifically here at binary ionic compounds. And binary there meaning that they're made up of two different types of ions. Okay, so we've seen that we need positive ions, negative ions to make ionic compounds. When we name the ions, when you put them together in the name of the compound, we want to do it in a particular order. So the name for our ionic compound is always going to be as follows. Okay, the cation name goes first, followed by the anion. Okay, the cation name is just simply whatever the metal is. So the metal name or the cation name. And then the anion name comes afterwards, and that will typically have the nonmetal with an IDE ending. Okay, so the best way to do this is to look at some examples. So for instance, if I am looking at the following compound, I have Na and I have Cl. Okay, so we typically write the name as the formula is written. So again, when we write the formulas, the metal or the cation is always written first. So Na is the sodium, and this is made up of the sodium ion. We don't put the word ion in the name. We just have sodium. And then Cl, you may be tempted to write chlorine. But as we saw earlier, you don't have chlorine. You actually have the chloride ion in it. So you have to change the ending, drop the INE, replace it with IDE. So this then becomes sodium chloride, would be the name for NaCl. Okay, similarly, if I have something like MgF2, okay, here I have the Mg ion, so this is magnesium. Okay, I don't put the word ion in the name. And then in F2 here, this means I have two of the Fs, and it's not just fluorine. Okay, this is an ionic compound. So I actually have the fluoride ion. So I drop the INE, replace it with IDE. So this then becomes magnesium fluoride. Okay, so you want to make sure that you pay attention to the naming, and we'll see a couple of wrinkles here that we'll address here in a second. So if I have my metal ion, so aluminum would just be aluminum ion or just aluminum. The Ba2 plus is barium. Ca2 plus is calcium. We see potassium K plus, zinc. 2 plus is just zinc. Lithium plus is just Li. What you'll also see is that there are some metals that actually can form different charges. So for instance, here you'll see copper with a charge of +1, and you also have copper with a charge of +2. And they're named differently. Okay, it's not, we can't just say copper because which one are we referring to? Copper with a 1 plus or copper with a 2 plus charge? So we need to incorporate Roman numerals in those names. Okay, so we do encounter situations where we specifically have now transition metals can sometimes form variable charge ions. We call them variable charge metals, for instance, meaning they can be different. So we need to use the Roman numerals in the name to specify the charge on that metal. Okay, so for example, we know sodium always in group 1 is going to have a charge of +1. We don't need to say to specify the charge. Similarly, magnesium in group 2 will always be +2. The transition metals in the middle of the table, they are a little bit trickier. So if I have something like, well, let's talk about Roman numerals first. Revisit what those are. So the Roman numeral for 1 is I. We put that in parentheses. Roman numeral for 2 is I. 3 is I. 4 is IV. 5 is V. 6 is VI. 7 is VII. 8 VII. 9 is IX. And then 10 is X. Okay, and if you're a fan of, for example, the Super Bowl, where they show, the Super Bowl number in Roman numerals, you're probably a little bit more familiar with this than other places, but these are the ones that we are going to use, that we're going to see in our class. Okay, so that's one thing to keep in mind when we do have transition metals. We're typically going to need the Roman numeral to specify the charge. So for example, if I say iron 2, right, what this means is that the charge on the iron is 2+. If I say iron 3, okay, this means it's Fe 3+. You might see in your textbook, and you might see other places, there are other ways by which they can be named. So for example, Fe2+ is also called a ferrous ion. Fe3+ is called a ferric ion. I'm not going to force you guys to learn this is an older naming system. Okay, I want you to know the Roman numeral naming system, because there isn't any ambiguity. If you see Fe2, you know it is Fe2+. If you see Fe3 here, right, you know that it is Fe3+, right? You don't have to memorize what ferrous or ferric means. So this would be iron 2, and this here would be iron 3. Okay, and that's how you would name them in a compound. So don't worry too much about the ferrous and the ferric nomenclature. That's an older system, but I mean, if you want to know it, you're welcome to, but I'm not going to force you to learn that for a quiz or an exam. You might see it on your ALEX, but I'm not going to hold you responsible for testing it, for testing you on it. All right, and then we have our anions names. So bromide, it'd be R-, etc., all the way down to sulfide, S2-. So keep in mind, you're not adding the IDE ending to your anions. You are replacing the ending of the atom with the IDE, right? So bromine becomes bromide. Nitrogen becomes nitride, not nitrogenide. Okay, hydrogen becomes hydride, not hydrogenide. Okay, so you're not adding the IDE, you are replacing the ending of the original element name with IDE. So you want to keep that in mind as we go through our nomenclature. So how do we come up with the formulas and the names for our ionic compounds? Well, let's take a look first of all at how we determine the formulas, okay? And the key thing about your ionic compounds and ionic formulas is that they need to be neutral, okay? So what this means is the charges on the cations, the positive things, must cancel out the anion charges. So anions are negative, cations are positive. They have to cancel. Okay, and we're going to write that ratio. That ratio that allows us to cancel out the charges would be expressed as subscripts in our formula. And for our ionic compounds, we want to get the simplest We want the smallest whole number ratios, which is referred to as our empirical formulas, right? The smallest whole number ratio. Okay, so this will involve a little bit of math. You want to make sure your positives, negatives cancel. There's a quick way in which to do this. And we can use a couple examples to illustrate the point. So for instance, if I have the sodium ion, which we know is +1, and the chloride, which we know is -1, when I combine these two, when you write the formula, the metal goes first, non-metal goes second. The quick way to do this to determine the ratios expressed as the subscripts is we can do something known as a cross-charge method, where the charge on the anion becomes a subscript on the cation. So the 1 here goes there, and the 1 on the Na becomes a subscript on the Cl. Okay, when you have 1s as subscript, we can omit them for simplicity's sake. They're understood. So this then becomes NaCl. That's the simplest whole number ratio. If I have something slightly different, let's say I have magnesium and I have Cl. So we know the Cl is -1. Magnesium's in group 2, so it's +2. I write this again, MgCl. The charge on the Cl here, and it's just the number now, not the sign on it. The 1 becomes a subscript on the magnesium. The 2 becomes a subscript on the chlorine. This then becomes MgCl2 as your formula. Okay, if I have something like Al, aluminum, and the sulfur, so Al is in group 3, so it's +3. Sulfur is in group 6, so 6 minus 8 is -2. If I combine these two, we have Al and S. The 3 here becomes a subscript on the sulfur. The 2 becomes a subscript on the aluminum. Okay, there's nothing simpler than that. I cannot get a smaller whole number ratio to show me the how they combine. Okay, and we can confirm this. Okay, if I have 2 aluminums, okay, 2, and the charge on the aluminum is what, +3, so that gives +6. I have 3 sulfides, so 3 times the charge on the sulfur is -2, so the sulfide is -2, that gives what, -6, +6, -6 are going to cancel out. Okay, the cross charge is a quick way to determine your formulas. Okay, there is a slight wrinkle to this. So for example, if I have calcium and oxygen, calcium we know is in group 2, so it's +2. Oxygen in group 6, 6 minus 8, -2. If I combine these two, I get CaO. The charge here becomes a subscript on the O. The charge there becomes a subscript on the Ca. So I end up with Ca2O2. And this is what we were saying before. When you come up with your ionic formulas, we want the smallest whole number ratio. Okay, so I have here a ratio of 2 to 2. I can simplify this. 2 to 2 is the same as 1 to 1. And I get that by just dividing by the smaller of the two numbers, which in this case is 2. So I end up with Ca1O1. And again, to clean that up, this just becomes CaO. Would be your formula for that combination. Okay, so the cross-charge method is a way that I suggest that you kind of quickly go through these, because you can come up with formulas really, really quickly without having to go through a lot of the math. Now, the math is not that complicated, but if you wanted to, you can do that. Okay, these are the combinations for your binary ionic compounds. Again, these are the simplest cases of ionic compounds that we'll see. And these are all made up of, all of the examples that we've looked at are made up of monoatomic ions. Okay, and monoatomic ions are things like what we've talked about, like your Ca2+, your oxide, right? These are charges on single atoms, or single atoms that have charges on them, right? So single there meaning mono, and then atoms, atomic. We will see examples of other types of ions a little bit later on.